So for this portion of the notes, I need you to have out the packet that I gave you in class that contains these slope fields. And this is the first page. Mine got a little cut off, but it starts with this sort of dot grid and then this filled in grid and then these filled in grids. So basically what a slope field is, it's a plot, a field or a plot of all the different slopes at all the different values of x and y for a particular function. And as we know, the slopes of the tangent lines are the derivatives of a particular function. And so the type of problem we would be confronted with would be something like this, where I'm given the derivative of a function. Because the derivative of a function, as we had talked about back in chapter 3, is the collection of all slopes of all tangent lines. Well, basically what we do with the slope field is we just plot that collection of slopes of all the tangent lines at any given point x. And in this case, we're going to go ahead and do that by making a table of values. Now notice that this slope dy dx is only in terms of x. So I'll just have a column for x and then a column for the slopes, dy dx. And I'm just going to use the x's that I have here, which go from -3 all the way to +3. And then I'm going to plug those x values into the equation for the slopes, which were x. So basically the slopes are equal to the values of x, so these are going to all be the same. So I basically come over here to this x value of -3, and I notice that the slopes are equal to -3 wherever x is equal to -3, which would be a steep negative slope. So I just kind of would draw a steep negative slope at all the values where x is -3. Then where x is -2, the slopes are going to be less steep, not as steep as -3, but still somewhat steep and negative. So I'd make a kind of slightly less steep, but still negative slope for where all the x values are -2. Okay, and so on and so forth. So where x is -1, now I have an even less steep negative slope. And then when x is 0, the slopes are 0, which means they're horizontal tangent lines. And then where x is 1, the slopes are somewhat steep and positive. Where x is 2, the slopes get steeper and also still positive. And then where x is 3, they get steeper and positive. In fact, I'm going to fix these a little bit. I kind of want these to be similar to these, just positive. So let me make them a little bit less steep. Okay, and then these here are going to have slopes of +3, so they're going to be as steep as these, but just positive. And there is our slope field for this particular collection of slopes, or this particular derivative. Now here's the thing. If I were to go ahead and solve for this function, this here is the collection of all the different possible graphs that this solution can have. And sometimes, like for example, in the homework, so this is sort of a side note, sometimes you'll be asked to, quote, sketch the curve passing through a particular point. And so for this example, I'll have it go through negative 3, 2. So sketch the curve passing through negative 3, 2. So we'd locate where negative 3, 2 is, which would be right there. And then you sort of follow the direction of the slopes. That's why it's also been referred to as a direction field. So if I were to follow the directions of the slopes, because remember these are supposed to be tangent lines, it would look something like this. Something like that. May not be exactly that, but something like that. Where all these, I'm trying to let these slopes sort of guide the direction of the curve, because these are the collection of all the different tangent lines of all the different points. Now notice, if I had been given a different point, so you could think of this as like the initial value. Notice if I'd been given a different point, my parabola could maybe be up here, or it could maybe be down here, because the constant changes. When you have a different initial value, it changes the constant. These slopes are the collections of all the slopes of all the possible antiderivatives, but as soon as you give it a point, that narrows it down to just one particular antiderivative. Now, what does this shape look like to you? Well, hopefully you're thinking it looks like a parabola. And what's the power of a parabola? Power of a parabola would be x squared. So that would be the antiderivative. Of course, there'd be a number in front of the x squared and then plus something possibly. But you can see that when the slopes are linear, or when the slopes, are of x, the antiderivative would form a parabola, would form an x squared of some kind. Okay, let's move on to the second one. So the second one sort of already drew the slope field for us. It says at the right is a slope field for this differential equation right here. The segments indicate slope at integer coordinates from -5 to 5, so that'd be from here to there. And also for y, from -5 to 5. It wants us to draw a possible graph for this solution passing through the point 0, 2. So we've been given the slope field, we've been given this initial value. So that's like right here, 0, 2. Follow the tangent lines basically to sketch what this curve would look like. So to me, it kind of looks like it's going to go up like that and down like that. Which looks like, maybe you're thinking the same thing, the graph of a third power, a cubic equation, which would be the antiderivative of a graph with the second power. Now this one here actually wants us to solve. So let's go ahead and use the same steps I used in the last video to solve this differential equation to see if our equation matches this graph. So step 1 would be to separate the variables. Step 2 would then be to integrate both sides. And also find the antiderivatives. And don't forget that combined constant. And here I'm just using the antiderivative formula from part 1 of the video, which is, this is n right here, x to the n, so this is n plus 1 dividing by n plus 1. Okay, so now I'm going to plug in my initial condition, which was 0, 2. So the y value is 2 and the x value is 0. So it turns out that c is 2. So the solution I get to this differential equation is y equals 1/3 x to the third plus 2. 1/3 x to the third plus 2. And if you look at this graph, it really does look like the graph of, or it is, in fact, the graph of 1/3 x to the third plus 2. And so all of these slopes here were the collections of all the derivatives at all the different points of x. This particular graph is the antiderivative that goes through this particular point. So you can really kind of see the connection here between chapter 3 and chapter 6. Chapter 3 is where we learned that derivatives were slopes of tangent lines to a curve. And if you put a collection of all those slopes together, you could easily make out the curve, basically. And here we're using our knowledge of antiderivatives to solve and figure out what function did I take the derivative of to get that. Well, I took the derivative of this function. That also happens to go through the point 0, 2 and be guided by these slopes. Okay, then the last part of this little practice worksheet is we're given 4 different slope fields, A, B, C, and D. We're given 4 equations down here. Equations who match these slope fields. So these are the collections of the derivatives of something, meaning the slopes of the tangent lines. These would be the solutions. These would be the solutions of those derivatives. So we want to look at the directions in which the slopes are going and see if they form these equations. So go ahead and take a second and see if you can figure it out. Well, notice anything that stands out or that looks familiar to you. And I notice this one right here is obviously an exponential type of curve because everything is going whoosh like that. So I'm thinking that D goes with B. Because if I graph 2 to the x, I'm basically going to get a shape that looks like this. This is definitely exponential. Okay, second thing that sort of stands out to me is this one. And I'm wondering if you can recognize what this looks like. Think back to Algebra 2 when we learned about conic sections. This here is a hyperbola. And its equation is right here. Anytime you have the x squared minus the y squared or y squared minus x squared, you get a hyperbola. And this particular one, since the x is positive, would be opening along the x-axis. So it would look something like this. It opens along the x-axis like that. Okay, now this is a familiar looking curve. It's known as the reciprocal function. And it's the function that has the asymptotes, and then you've got the opposite facing curves. So that looks to me like this is going to go with A. So B went with capital A. And then little a goes with capital D. Because you've got the asymptotes here, and then the alternate facing curves. So basically these slope fields are giving away what their original functions were. Okay, the last one, which is maybe a less of a familiar equation, but we do notice something about it. It's got that x squared in there. Even though it is e to the x squared, it's got the x squared, which tells me that this is going to be an even function. What makes that important is that it's going to basically have y-axis symmetry. Because no matter if I plug in a positive or a negative x, the y values are going to be exactly the same. Because I'll be squaring the positive x's, which make positive numbers, and then I'll be squaring the negative x's, which also make positive numbers. So regardless of whether x is positive or negative, the y values are going to be 100% identical. And so you have the same thing over here that you have over here. So little c goes with big C. And you've got the graph of e to the x squared, which makes some kind of parabolic graph. You got that x squared making it parabolic. So this is just some practice in seeing how the slope fields basically take on the shape of the functions that they are solutions of. Okay, then the next page. The next page of your packet is very similar. Creating a slope field, and this kind of walks you through the same problem with 5 steps. But this is a little more advanced in the sense that now my derivative has both an x and a y. Not just x like the last handout. This derivative has both an x and a y. So when you go to make the slope field, which this worksheet basically walks you through, notice that the table of values has a column for x and for y and for the derivative. Notice that it has a column for all 3 because your derivative is now going to depend on both x and y. So for example, at the point 0, 0, you have one kind of slope, where at the point 1, 0, you have a different kind of slope. At the point 0, 1, yet a different kind of slope, and so on and so forth. Okay, also notice that at 0, 0, they don't say undefined. They say indeterminate because I'm dividing 0 by 0. That's different than in this case where x was 1 and y was 0 and I was dividing 1 by 0. That's what we call undefined, and that's actually a vertical tangent. Whereas this is indeterminate is no tangent at all. And that is why at 0, 0, they don't have any tangent line at all. Okay. And then when it's undefined, at 1, 0, they have a vertical tangent. And when it's 0, like at 0, negative 1 right here, they have a horizontal tangent. And then this is just a steep negative, steep positive, and so on and so forth. Okay, so they basically create this table of values, begin plugging in all the different slopes, and eventually arrive at this slope field, which should be looking very much like circles. Very much like circles. And so now for step 4, it wants us to solve. It wants us to solve this differential equation by separating the variables. And it wants us to let the square root of k be the radius of the circle. Sorry, mine got a little bit cut off. So let's go ahead and do that. And I'm going to just sort of use this space right here since it's available to me. So I'm going to begin by separating the variables. So this time I need to also move the y over here with dy, and then the dx over here with negative x. So I'm going to have y dy equals negative x dx. So that's step 1. Step 2 is to take the integral of both sides, which is also to find the antiderivatives. So we'd have y squared over 2 equals negative x squared over 2 plus a constant. And right here I just use the constant multiple rule where you just find the antiderivative separately and then multiply by the constant. And then we will go ahead and plug in the initial condition, which they did not give me an initial condition, so I just basically solved the differential equation. So notice it said solve the differential equation as opposed to the initial value problem because I wasn't given an initial condition. And so let's just go ahead and multiply by 2 to both sides. So I get y squared equals negative x squared. So now this c has been multiplied by 2, so it's a different constant now, and I'm just going to go ahead and use the one that they gave me here. Let's just call that k. And then I'll go ahead and add x squared over to the other side. So there's our solution to the differential equation. Since I wasn't given an initial value, I don't need to solve for k. We just understand that the square root of k would be the radius of the circle. So this is the collection of all different circles with all different radiuses. And so here in 5, they're just kind of showing you, here's some sample solutions. Here's a radius of 1, a radius of 2, a radius of 3, and so on and so forth. So in other words, k can be anything, And the slope field indicates that as well. And it makes a comment here, there's an infinite number of such circles we can draw because there's an infinite number of possibilities for K. So that is a little bit on slope fields and how they are tied in with differential equations. And in our last video, we're going to actually solve an AP test free response question.